Good afternoon, class. We are looking at Chapter 3, Derivatives, Section 3.3, Basic Differentiation Formulas. So we covered derivatives and rates of change, derivative as a function, and now we're going to look at basic differentiation formulas that are given here, and we go over them in a moment. First, reminding everybody that when we have two pairs, rise over run is the slope. In essence, the average rate of change of y with respect to x, or the slope of a secant line, the blue line. If you want to find the slope of the red line, then we take a limit and we let q approach p, x approaches a, h approaches 0, and it becomes the slope of a tangent line. We call it f prime of a, and this is just a point slope formula, nothing brand new. And this is the differentiation formula. First, the Leibniz's notation and the general format. Now, going over the basic differentiation, we start with f of x being a constant. So we want to find the derivative. There are a couple of ways to approach that. One of them is that any constant, y equals c or f of x equals c, represents a horizontal line, in which case the slope is 0. So any horizontal line in the form of y equals a number or f of x equals a number, we know the slope is 0, so f prime of x is 0. If you want to go with the definition, we just plug in, and since f of x is independent of x, when you plug in x plus h, or anything else makes no difference, it gives you c back. So it becomes c, the limit of c minus c over h as h approaches 0. Now, the numerator is always 0, and the denominator is approaching 0. Nevertheless, it is not 0. And 0 over any number, no matter how small, it is 0. And that's a proof by definition. Therefore, the derivative of any constant, any number, is 0. I want to remind you of the interest formula that we learned. I equals PRT. We learned it in algebra. And the amount is the sum of the P and I. So I is the interest, P is the principal, R is the rate, T is the time. Same thing happens here, but this is being compounded, and N represents the number of times it gets compounded per year. So if it's annually, N is 1, semi-annually, it's 1/2, quarterly is 4, monthly is 12, so on and so forth. So if we decide to represent the reciprocal of R over N with some other variable such as M, what happens is that we are going to replace this with 1 over N, and then the cross product here shows that N is R times M. So we can replace this with R times M. We put the M intact and then R next to T, and it looks like this. The reason we separate this, and this is what we've done in algebra, to say that now if we compound it indefinitely, continuously, becomes P e to the power of RT, and therefore This is E. So what does it tell us? What we learned in algebra, and that is that E is the limit of this expression 1 plus 1 over m to the power of m as m approaches infinity. And sometimes they use just any other variable like x, like n, you name it. So you can, as long as this one are the same, you can use any variable. If we let 1 over m be h, so if we replace this with h, then m will be 1 over h. When m goes to infinity, 1 over m or h goes to 0, which gives rise to this expression. And E is not a missing value. It's been found to be an irrational number like pi, that it continues indefinitely, 2.7182818, and it continues indefinitely. So we have this definition. And again, as I mentioned, you can use any variable here. We had m here, you can change it to n or x, and that's fine. And this definition of the limit of e to the power of h minus 1 over h as h approaches 0 equals 1, that's another way of discussing the number e. We will get to that later on, and we'll show the definition. For now, so the power rule says the derivative of x to the power of n, we bring the n down, we make it a coefficient, and the exponent goes down by 1, subtracted by 1. Which means if I want to find the derivative of x according to this, then remember x means x to the power of 1, so it will be n1 times x to the power of 1 minus 1, or 1 times x to the power of 0. You know this is 1, and the answer becomes 1, and that's how we arrive at it if we use the power. The constant multiple, you can take the constant out. The derivative of the sum is the sum of the derivatives, cut them into 2 pieces. The derivative of the difference is the difference of the derivatives, cut them into 2 pieces. And here's the table you should know. The derivative of a constant is 0. Power rule says the derivative of x to the power of n is n x to the power of n minus 1. The derivative of k times x, where k is a number, is a constant, is k. The derivative of e to the power of x is itself is e to the power of x. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tan x is secant squared x. The derivative of cotangent is minus cosecant squared x. The derivative of secant x is secant x times tan x, and the derivative of cosecant x is minus cosecant x times cotangent x. Let's look at the proof for the power rule. You're not responsible for that. But if you can follow it, it makes it easier to understand the concept. So to prove that the derivative of x to the power of n is n x to the power of n minus 1, we're going to go to the basics. That means the definitions. And to do that, there are a couple of things we need to do. We plug in x plus h here, and we get x plus h to the power of n. This one is clearly x to the power of n. And to do this, we need to expand this. To expand this, I want to remind you of 2 things. One of them is the concept of a factorial. N factorial means pick a number, which is a whole number, by the way. And if you want to find the factorial, you multiply by the previous numbers. And of course, 0 factorial and 1 factorial are 1. If you are looking at an example of, let's say, 5 factorial, means 5 times 4 times 3 times 2 times 1, 5 times 4 is 20, times 3 times 2 is 120. That's the meaning of a factorial. Then we have a binomial theorem here. And it says if you want to expand it a plus b to the power of n, then we have a combination of n choose 0, a to the power of n, b to the power of 0. By the way, b to the power of 0 means 1. A combination of n 0 means 1. I will show you in a moment. And then combination of n choose 1, a to the power of n minus 1, b to the power of 1. And we continue until the last one where it's the combination of n choose n, a to the power of 0, b to the power of n. This also becomes simply b to the power of n. So it becomes a to the power of n, the first one, and the last one becomes b to the power of n. So this is the combination formula CNR parentheses n comma r, or simply NR, the way they have it. That is the combination of n elements or objects, distinct, pick, or different elements. So for example, if I want to look at Cn0, it becomes n factorial over 0 factorial, n minus 0 factorial, which becomes n factorial over n factorial, and it's equal to 1. I want to look at this one also, Cn1, because that actually plays a very important role here. According to this formula, of course, n factorial over 1 factorial, n minus 1 factorial. So as you can see, the denominator is n minus 1 factorial. The numerator is n factorial, which means I'm going to write it as n times n minus 1 factorial, and therefore the answer is n. And you can show that this is also equal to 1. I leave it for you to try that. So now let's actually expand and see what happens. Before I do the expansion, I want to give you another example of a binomial theorem that you've already seen. For example, a plus e squared, b squared is a squared plus 2ab plus b squared. That's a binomial theorem. Or a plus b cubed, you may remember, is a cubed plus 3a squared b plus 3a b squared plus b cubed. So these are stuff we have seen in algebra. I hope everybody remembers them, and we're going to move on from here. So let's do the expansion here. So we're going to expand this using this concept. And this is x to the power of n. So this part becomes this. And by the way, this one is really, this one is Cn1, this is Cn2. It can be shown that it's equal to that. So first of all, these two cancel each other, and we are left with the rest of it. So everything inside the brackets remains except x to the power of n, which has been canceled out. So we are going to factor the h out. When we do that from the top, this one has n x to the power of n minus 1. This one the h squared becomes h. We are factoring out the h. You can distribute the h and it must give you that. You continue towards the end, n minus 2, when we take from n minus 1, when we take the h out, becomes n minus 2. From n becomes n minus 1. So 1 h goes down. And I want you to notice that this is equal to that. So notice this notation is equal to this, and you can expand it following the combination formula to see that. And so now we can cross the h out from here and here. And we are left with what's inside this parentheses in red. And now if we apply the h equal to 0, this becomes 0. This becomes 0. This becomes 0. Everything goes to 0 when we apply h equal to 0, except the first one, and therefore the answer is n x to the power of minus 1. In other words, that's the proof. Let's look at a few simple examples of the power rule. I start with the first one. So if I want to take the derivative here, I make the exponent to be the coefficient, and the exponent goes down by 1, and we get 6x to the power of 5. So it's very straightforward. And I'm just reminding you of the formulas we're going to use. So what do you think we get here for part B? $1,000 becomes the coefficient, and then the exponent goes down by 1. And we get 1,000 x to the power of 999. You don't have to write that step if you are comfortable with the concept. What about part C? Anybody? Four becomes beautiful. 4 becomes the coefficient. The exponent goes down by 1. There you have it. Now, it is important to know that the independent variable doesn't have to be x. It can be any variable. In this case, the independent variable is t. That's why y prime here is the same as dy dt, whereas y prime here, we could have said dy dx. All right, let's look at this one. Part D, what do you think the answer is here?
It's R.
Perfect. So we keep the coefficient as it is, and then r squared becomes 2r. And again, notice we use dy dr to emphasize that the independent variable is r. This is in Leibniz's notation. Part E, what's the answer here?
$60x to the fifth.
Beautiful. So this part is 6x to the power of 5. So again, whether you want to write the intermediate step or not. This is a simple question, you don't have to. Let's give everybody a minute to come up with the answer for the last one on this page. F of x is x to the power of 8 plus 12x to the power of 5 minus 4x to the power of 4 plus 10x cubed minus 6x plus 5. So we want to differentiate this, and we are going to do this term by term. So we want to differentiate this. F prime of x equals, the first one, x to the power of 8 gives us
8x to the 7th.
8x to the power of 7 plus
60x to the 4th.
we multiply the 12 and 5, we get 60 x to the power of 4 minus
16x cubed.
16x cubed, because 4 times 4 is 16 minus 16x cubed plus
30x squared.
30x squared minus,
6.
and that's it, because a constant gives you 0. So this one is 8. Let's actually fix it right here. So that's the final answer for this one. All right, part A, very straightforward. We want to differentiate that. 5x gives us 5, and a constant gives us 0. Simply put, the answer is 5. However, if you want to do part B, the way it's given, we cannot use the power rule. So we are going to rewrite this as 2x to the power of negative 1, and therefore we can use the power rule here. So now that we wrote it in this format, we're going to say 2 times negative 1, which is minus 2, x to the power of, so let's just write this. So now f prime is 2 times negative 1, x to the power of minus 1. We're going to subtract 1 more, which becomes minus 2x to the power of negative 2. To rewrite it properly, this becomes negative 2 over x squared. Part C is very straightforward. 7 times 2 is 14, so 14x, and the constant 4 simply gives you 0. So this is 7 times 2, x to the power of 2 minus 1. All right. In order to do part D, again, first and foremost, we have to do an algebraic step. By the way, there are many algebraic steps as we go through the process, but there's always one calculus step. What would you do first? What would be your algebraic step here, part D? What should we do first?
Change the radical.
To x to the power of 1/2. And then to distribute, please understand this has exponent 1. And when we distribute it over the parentheses, becomes x to the power of 1 plus 1/2, or x to the power of 3/2 plus 5x minus 2. That's algebra. Now, the calculus step is here. F prime is 3/2. X to the power of 3/2 minus 1 plus 5x gives us 5. And that's it. Now 3/2 x to the power of 3/2 minus 1. This is the only calculus step. I'm going to put the asterisk next to it. Now I'm going to rewrite this as 3/2 x to the power of 1/2, or 3/2 square root of x plus 5. Can anybody tell us the answer for here? G dx of pi squared, what is that equal to?
Zero.
Perfect, because you're dealing with a constant. It's important to know if I change this to any number, pi squared, e, 1.5, 2/3, or 10,000, makes no difference. It's a constant, the answer is 0. Same thing happens on this page. First, we have to do algebra. So for example, the first one, I have to change it to x to the power of -5. Now I can use the power rule, -5, x to the power of -5, minus 1, which means -5 x to the power of -6. And we rewrite it properly. So notice, this is the only calculus step. Everything else, algebra. We're going to do the same thing to part B. We are going to rewrite it first. How would you rewrite this? In other words, algebraically. How would we rewrite part B so we can use the power rule?
Change x cubed to x negative cube 3.
Perfect. We bring the x cubed up. We make it x to the power of -3, which is an algebraic step. We are ready to move on to the one and only calculus step. F prime of x equals 2/7 times -3 x to the power of -3 minus 1. Now algebra, -6/7 x to the power of -4. And here's the final and proper answer. If you want to skip any of those algebraic steps, that's fine. Which brings us to part C. And we have to do our algebraic technique first so we can use the power rule. So we are going to rewrite this as what? F of x is 2/9 x to the power of -4. I hope you realize that this cancels out this one and gives us x to the power of 4 in the denominator. We bring it up, and now we are ready to do the only calculus step, which is 2/9 times -4 x to the power of -4 minus 1. And again, I box this. This is the only calculus step. I continue with my algebraic steps, minus 8 over 9 x to the power of negative 5. And one more algebraic step gives me the final answer. Again, we have to use algebraic steps so it becomes possible to use the power rule. This one, the first one we've seen, we're going to rewrite it as x to the power of 1/2. F prime is 1/2. X to the power of 1/2 minus 1, or, and again, this, the only calculus step. And I want to emphasize this because I want to make sure everybody understands that calculus is not too bad. We have many algebraic steps and we have to be very comfortable with that. Now, x to the power of negative 1/2 goes down, becomes positive 1/2 or a square root. The next one, again, algebraic technique, will rewrite it as 2x to the power of 4/5. So f prime is 2 times 4 over 5 x to the power of 4 over 5 minus 1. We get to the algebraic step again, 8 over 5 x to the power of negative 1/5 goes down, becomes positive 1/5 or the 5th root of x. Now, those of you who've heard of the quotient rule, if anybody wants to do this by the quotient rule, later on we discuss that, not a good idea. There is an easier way to do that. Anytime the denominator has one term or maybe even one algebraic, term, you can do the division by cutting this into two fractions. This part gives you 10. The second fraction gives you minus 7x. And clearly the answer is minus 7. You really don't have to do much. And that's the idea. You can easily come up with the answer. Know your algebra, and it can speed up the process. If you want to go by the rule that we discuss in the next section, it takes much, much longer. Now that we have learned the easy way out, if we are finding the equation of a tangent line, we are going to do the same thing. In order to find the equation of a tangent line for the function f of x equals x squared minus 3x minus 1, we need two things. We need a pair x comma y, and we need the slope. So let's discuss the pair. If x is 4, what is y class? Anyone? How would you find the y coordinate for this case?
It's 3, plug in 4.
Beautiful. When you plug in 4, you get 4 squared, which is 16, minus 3 times 4, which is 12. That gives you 4, minus 1, is 3. Now to find the slope, first you have to differentiate. F prime of x is simply 2x minus 3. And now if I plug in 4 into this, 2 times 4, 8 minus 3 is 5. That is the slope. So 4 into f prime of x gives us the slope. 4 into the original function gives us the pair. We use the point slope y minus y1 equals m times x minus x sub 1, which means y minus 3 equals m, which is 5, x minus x sub 1, which is 4. The right side is 5x minus 20. If I add 3, it results in the line or tangent line of y equals 5x minus 17. By the way, the pair belongs to the function as well as the tangent line, so it should work out here too. Next, we want to find the point or points for which the tangent lines are horizontal. So first, when we are interested in finding the tangent line, we are interested in finding the slope, which means we need to find f prime. So first thing first, we find f prime because it mentions tangent line, which is 3x squared minus 6x. Then we know every horizontal line has a slope which is 0. Since we are looking for tangent lines that are horizontal, this must be equal to 0. And we are going to solve this, which means it's a simple algebraic equation. We factor out the common factor of 3x, and x becomes either 0 or 2. And by the way, whether it's 3 or 3000 or negative 1/2 has no bearing on the solution. There are two solutions. X is either 0, you plug it in, you get the pair 0, 5, or x is 2, you plug it in and you get 1. So make sure you plug into the original equation to find x and y coordinates of the pairs. In other words, we don't want to be under the assumption this is a pair, 0, 2. No, 0, put it into the original function, gives you one pair. 2, put it into the original function, and it gives you another. The next thing we want to look at is the exponential function, and we know that the exponential functions are in the form of f of x equals a to the power of x. Where a can't be 1 and it must be positive. So we want to find the derivative, so let's go with the definition. And it becomes a to the power of x plus h minus a to the power of x over h, and we are going to simplify this expression. So limit as h approaches 0, a to the power of x plus h minus a to the power of x over h. The top, this one is a to the power of x times a to the power of h. And therefore, we can factor out a to the power of x, which gives us a to the power of h minus 1. Because the limit applies to h, and a to the power of x is independent of h, we can take it out. And so if f of x is a to the power of x, f prime is the same thing times some limit. What if we have a base a, some base a, such that this portion becomes 1? If there is such number, that this becomes 1, then f of x becomes identical to f prime of x. So is there an a, is there a base such that this limit equals to 1? That's what we are looking for, because if it is, f of x becomes equal to f prime of x. This is done numerically. They look at various numbers. For example, they look at number 2. So look at this expression. Look at this expression. Replace the a with number 2. Becomes 2 to the power of h minus 1 over h. And as far as h is approaching 0, we start with 0.1, make it smaller and smaller, and even smaller, closer to 0. And there seems to be that the limit is going towards this number, 0.69. Let's do this to number 3 also. Seems to go to 1.10. Therefore, you say this column gives rise to, if a is 2, f prime of, by the way, this is also f prime of 0, we discussed that, gives rise to this limit to be 0.7 or 0.69. For number 3, then it's 1.1. So we haven't found the number yet, but this says the number is somewhere between these two. That means the number is between numbers 2 and 3. And it's closer to 2 than 3. So E is the number such that this is equal to 1. This is a definition of E. And we, with a lot of numerical analysis, they end up with the answer, which is almost 2.718. And so we get the following. Notice if we have f of x equals a to the power of x, and if we let x be 0, look at this one. If you choose x to be 0, you get a to the power of 0, limit of a to the power of h minus 1 over h. This is equal to 1, and it gives you this limit. Therefore, f prime of x, regardless of what a is, becomes f prime of 0 times a to the power of x. This, the significance of this is that if you have different exponential functions, the only exponential function whose slope equals 1 at the intercept 0, 1 is y equals e to the power of x. Again, this is something we discuss in calculus. You don't have to worry about this so much. So when f of x is a to the power of x, f prime is this. If we replace the x with 0, we get this one, and f prime for any function of the form a to the power of x becomes f prime of 0 times a to the power of x. And for e to the power of x, this is 1, so they become identical. So this is the definition we saw in algebra. We went over that also in the beginning. And this is the definition we just went over, the proof, the limit as h approaches 0 of e to the power of h minus 1 over h equals 1. But what matters to us is what comes next. If f of x is e to the power of x, so is f prime of x. That's all we need for us. So with that being the case, if f of x is e to the power of x minus x, we want to find f prime and f double prime. So starting with the function, let's find f prime. Well, let's take the derivative piece by piece. The first one is e to the power of x minus x gives us 1. So the answer is f prime of x is e to the power of x minus 1. And if I want to go to the second derivative, if this is f prime, f double prime is the derivative of the first piece, which is itself e to the power of x. And this is a constant, doesn't give us anything except 0. And so the answer is f double prime is e to the power of x. All right. Again, the derivative of sine is cosine. The derivative of cosine is negative sine. So this gives us cosine. Very simple. and this gives us plus pi times cosine gives us negative sine, and therefore the answer is minus pi cosine t minus pi sine t. To differentiate the next piece, first let's change the fourth root of t to t to the power of 1/4, so we can use the power rule. So the first one becomes 1/4 t to the power of 1/4 minus 1. The second piece is itself minus 4 e to the power of t. I want to make sure everybody can see what happens here. This one, you have negative and the denominator is 2. That means negative 1/2 is the coefficient, so nothing happens. But what happens is to cosine is that cosine, the derivative is negative sine. So negative times negative makes it positive. This is negative 3/4. So this one we can write it as 1/4 t to the power of positive 3/4, which becomes 1/4 the fourth root of t cubed. The rest are straightforward. We've seen this question before. I've made a slight change and you'll see in a moment why. The distance in meters of an object from a starting point is given by s of t equals 2t squared minus 5t plus 4d, where t is time in seconds. What is the velocity of the object from 2 to 4 seconds? This is elementary algebra. This is the average rate of change. That means total distance over total time. So that part, we've seen it before. So V average, change in distance over change in time. So S of 4 minus S of 2 equals 4 minus 2. I hope you remember we did this. So 52, you plug in 4, you plug in 2, get 52 minus 38, and the denominator is 7 meters per second. So this is basic algebra. The next part is asking for the instantaneous velocity, and we have already done that, but we did it with the definition. Now we want to take the easy way out, and to find the velocity, it's s prime of t, which makes it 4t minus 5, and to find it after 6 seconds, let's plug in 4 times 6. 24 minus 5 is 19 meters per second. So really not much brand new here. The only thing added here is the acceleration. Acceleration is the second derivative of the position function. That means a of t is s double prime of t, or the first derivative of the velocity function, the v prime of t. So that means if I want a of t, I need to differentiate this, and I get 4. So a of t is v prime or s double prime, and it's 4 meters per square second. I will discuss the units in a moment, but because this is a constant, regardless of what the time is, it's independent of t, so you don't have to plug in because it makes no difference after 6 seconds or 10 seconds or 2 seconds, still has the same answer. So why is it meters per square second? This is the s dt, the change in position, over change in time, and it makes it meters per second. whereas this one is dv dt, which has the units of meters per second for the velocity, seconds for the time, meters per second becomes meters per square second. Now, the next one is asking, when does the object reach a velocity of 31 meters per second? This is the velocity. We set it equal to 31 and solve. So for t minus 5 equals 31, we move the negative 5 becomes positive 5. So 36 divided by 4, and t becomes 9 seconds. And that's the final answer.